So our next speaker is Dr. Sara Seager from MIT with a presentation on biosignatures in Venusian atmosphere. Dr. Seager, you're ready to start?
Hi, everyone. Good morning, good afternoon. I am here to tell you about the planet Venus. And 1 year ago, almost just over a year ago, I was part of a team that announced the detection of phosphine gas in the atmosphere of Venus. I'm going to come back and talk about that in a moment, but I'd like to start with the backstory. That starts a very long time ago, billions of years ago, when a simple, humble life form, cyanobacteria, figured out something very clever: how to harness energy from the environment, photosynthesis, and in the process gave off oxygen as a waste gas. And eventually, oxygen gas filled our Earth's atmosphere to 20% by volume. Now, oxygen is incredibly reactive, so it shouldn't be in our atmosphere at all. Without vegetation today and without photosynthetic bacteria, our atmosphere would have virtually no oxygen. What I like to think about is, mostly I work on exoplanets, but I like to imagine an intelligent alien civilization orbiting on a planet orbiting a nearby star with the kind of telescopes we're hoping to build. If they look at Earth, they'll know there's life here, or they'll suspect there's life here. And that's not from city lights or from things like the Great Wall of China, but it will be from oxygen gas. Now, as a scientist, I have this one quote I found some years ago that has really stayed with me and is one of my guiding principles. Nothing would be more tragic in the exploration of space than to encounter alien life and fail to recognize it. And why this weighs heavily on me is because, true, our Earth has oxygen, a fantastic biosignature gas, but our Earth has only had a significant amount of oxygen for 1 billion years. Now that sounds like a long time to a lot of people, but given that our Earth has been along much longer, I constantly think about, and my whole team is working on literally every single plausible gas that might be something we should think about that could be a biosignature gas on exoplanets. And while my team was working on this, we came across a really intriguing gas called phosphine, a phosphorus atom and 3 hydrogen atoms. Now on Earth, phosphine is only associated with life because, we have hardly any hydrogen on Earth. Phosphorus wants to go with oxygen atoms in the form of phosphate. And at the temperatures and pressures here on Earth, and even on the surface of Venus, it's just thermodynamically highly disfavored to make phosphine. Now, the discovery of phosphine on Venus is very controversial. It's not resolved yet. My team stands by the discovery. Other teams have looked at our data, analyzed our data, and have not found a signal. Other teams have reanalyzed the JCMT data and have seen a signal, but are pushing sulfur dioxide instead of phosphine. We stand by phosphine because if it was a sulfur dioxide line, we'd have to have way more sulfur dioxide than ever seen before. My talk isn't about phosphine, but I'll leave you with one more item on phosphine. And that is that Rakesh Moghul and team have been independently reanalyzing NASA Pioneer Venus data from nearly 4 decades ago, and they see signs of phosphine as well. So we're just going to have to let this play out. And in the meantime, I'm going to tell you about a bunch of other things. But first of all, Venus is actually a terrible place for life. We all know that the surface of Venus is so hot enough to melt lead. We were just hearing about Mars and Mars analog like Venus. We don't want to simulate the surface of Venus and ever imagine us humans going to the surface. And this is, of course, due to Venus's massive carbon dioxide atmosphere. But nonetheless, since Carl Sagan over half a century ago first put this idea forward, people have been speculating about the idea for life in the clouds, because about 50 kilometers above the surface, Venus is cool enough. Just like here on Earth and most planets, as you go above the surface, it gets colder and colder. And there's a layer in the clouds of Venus where the temperature is just right for life. And there's energy and there's liquid and there's other things that we all usually agree that life needs. Yet, even in the cloud layers, the clouds are incredibly acidic. They're made of concentrated hydrosulfuric acid that is way more acidic. Like, honestly, it's orders of magnitude more acidic than the most acidic environments we find life on Earth. And it's also very dry in the atmosphere, drier, 50 to 100 times drier than the driest place. So you might wonder why we're thinking about life on Venus, because it's so incredibly compelling. And Venus is not too far away. It's not too hard to get to. And so myself and a lot of others just want to sort of are actually reviving this idea that Venus could be an astrobiological target. So there's some new work I'll touch on. Some of it's published, some isn't. Jan Spacek and Steve Benner published a paper showing that if you start with a simple organic molecule, like perhaps formaldehyde, that might come from meteorites, for example, in concentrated sulfuric acid, this small organic compound can react to produce a more complex organic set of chemistry, actually. And this is something people know about in industry, where they use concentrated sulfuric acid and their components they call red oil. This is the petrochemical industry. So in fact, there could be a lot of rich things happening in these sulfuric acid droplets, not necessarily related to life. The second topic I wanted to briefly mention is Daniel Dudovich at Harvard has been working in the lab, and he has shown, it's not published, but he's showing that certain lipids can self-assemble into a spherical shell in concentrated sulfuric acid. So if there is life in the clouds of Venus, in the droplets, perhaps it has an acid-resistant membrane. And third, what I'm going to talk about today may seem equally out there to you, but it's the idea of biological neutralization of these acid droplets to levels that are more acceptable for biological materials. So it turns out that here on Earth, there are actually examples of some life inside stomachs. You know, in your stomach, it's incredibly acidic. The acid breaks down food. And this life secretes ammonia, these microbes, to neutralize like a droplet-sized acidic environment. So I'm going to walk you through a sort of series of atmosphere anomalies, and then I'm going to, like at the big picture level, present a model that ties these together, that relies on life in the atmosphere. Okay, so just starting somewhere that people in the audience might be familiar with is this picture of Venus here. This is an ultraviolet image of Venus, and see those dark stripes? These are, we don't know what is causing these dark stripes specifically, what the composition of the so-called anomalous ultraviolet absorber is. But whatever these particles are, they are absorbing like 50% of all of the ultraviolet light that falls on the planet. So this is really intriguing. This isn't related to the theory I'm going to tell you about, but I just want to start out with this because it is something quite curious. So what I am going to do is show you a series of plots like this. This is showing you the altitude above the surface on the left side, on the y-axis in kilometers. On the right side, I'm showing you pressure in bar, and also it looks like temperature in Celsius. And these dots, they just represent clouds in the cloud layer of Venus. It's kind of just a cartoon, but I have some text here to go along with it. So another really intriguing, I'll call it anomaly or unexplained thing on Venus, is that in the lower cloud layers, there are larger particles that appear to be non-spherical. And why this is so intriguing is if it's not spherical, it can't be pure concentrated sulfuric acid. In fact, there has to be some more complex chemistry in the droplets. That, of course, doesn't mean there's life, but it's certainly intriguing and something that we'd like to be able to revisit on Venus. Okay, so interestingly, the Venera probes have seen quite a lot of phosphorus and iron detected in the cloud layers. And this is important because life, if it's there, it needs metals and other non-volatile elements for catalysis. At least life on Earth does. Now we come to a slightly more complicated situation that we do have a paper under review, by the way, but I'm going to try to somehow succinctly capture it all. But it turns out that if you go back, and this is done recently by Paul Rimmer, and look at all the different measurements and see like what people have explained and what has been left unexplained, it's quite an interesting story. So first of all, there is some, and by the way, I have this little code at the bottom if you want to decode what all these molecules are. First of all, there's been oxygen measured in small amounts to about part per million levels in the cloud layers. And this was done independently by both the Russian Venera probes and also by the NASA Pioneer Venus probe. That's kind of curious and nobody knows why it's there. There's actually a very tentative detection of ammonia gas, which really does need to be confirmed. Then there's also a tentative detection of methane and other hydrocarbons. Those are most likely contamination. But in this model, if you're looking and decoding these molecules, I'm also showing you some water vapor and some sulfur dioxide. And these are really known to be present, but their abundance profiles, how they change vertically in the atmosphere and the cloud layer, is actually not explained at all. And so my team built upon, okay, so let me see, I think I've got to back up for a second, but there's been a recent paper by Paul Rimmer. He's from Cambridge, UK. And he had this really interesting idea. He postulated that perhaps salts are getting uplifted from the surface, and these salts get absorbed by some of the cloud droplets. And in the process, they act as a buffer and partially neutralize the cloud droplets. They're still very acidic, but not as acidic. And then sulfur dioxide gets absorbed into these cloud droplets, and there's then a kind of deficit of sulfur dioxide in the atmosphere. So I'm now going to talk about only this plot on the left here, which comes out of a photochemistry model. This is about sulfur dioxide, so I'm going to walk you through this. On the left side, this is height above the surface in kilometers, and the x-axis is mixing ratio, which if you don't know what that means, it's the kind of weird jargon just for like a volume ratio of a gas. I'd like to draw your attention to this dotted purple line, which is sulfur dioxide in a base model of the atmosphere with photochemistry. So I want you to think about sulfur dioxide coming out of volcanoes on Venus and populating the atmosphere, mostly uniformly until a very high altitude where ultraviolet radiation would destroy sulfur dioxide. But that's not what we see, which are these gray points. The gray points with uncertainties, those are actual measurements, okay? So what you're seeing is not the sort of uniform sulfur dioxide, but in this cloud layer here, between about 48 and 60 and higher kilometers, there's actually a depletion of sulfur dioxide. If you read it off this x-axis, it is quite a lot, actually, a few orders of magnitude. Now take a look at this dashed line. And the dashed line is actually a model that assumes artificial fixes to match the data. And if you dig into the literature on Venus's photochemistry models by people, pretty much everyone has to do this, has to have some kind of artificial fix to fit both sulfur dioxide and water vapor. Now I'd like you to look at the solid line. It's not obviously a perfect fit, but this solid line has no artificial fix to the data. This solid line makes a bold and out there assumption that there's life in the atmosphere of Venus. And I want to walk you through this theory because it's a little specific. And then I'm going to give you some general discussion. So you can just sort of look at the bullet points on the left, the image on the right. The image on the left is just illustrating some of these molecules. So there's oxygen present at tens of parts per million. There's a possible presence of ammonia in the atmosphere. The vertical abundance profiles of sulfur dioxide and water vapor are not well explained. And there's an unknown lower cloud large particle composition. The hypothesis we're putting forward is there's life, some kind of microbial type life in the clouds producing ammonia. Now, we don't know for sure if ammonia is in the atmosphere, but it might actually be there. This ammonia gets absorbed into the cloud droplets, some of it, and neutralizes the droplets to less acidic than the droplets are without ammonia. The droplets trap dissolved sulfur dioxide. And curiously, the most energy efficient way for this hypothetical life to produce ammonia, the reaction also generates oxygen. So as a consequence of this idea, we actually resolve all of these listed atmosphere anomalies. And some of the droplets are predicted to be what we're just calling ammonium salt slurries. So what I like to say about this theory, and by the way, we have a paper under review. If you'd like a copy of the paper, I can send it to you as long as you don't share it around. Just send me an email. So I just want to say one thing at this point. I gave you a very quick high-level summary. I look at this situation as pick your poison. You can explain the data by artificial fixes to your model. You can imagine so much salts being uplifted from the surface, way too much that makes physical sense to neutralize the droplets, and then after a cascade, explain the profiles of sulfur dioxide and water vapor, but that doesn't help with ammonia and oxygen. Or you can pick the more out there concept of life in the clouds, which it has to be producing ammonia, and then it has a cascade effect to explain all of these things. Well, the great thing about Venus is we can go there. And indeed, NASA is planning to go to Venus with 2 different missions. ESA is planning as well. But to my knowledge, they're not looking for any of these things. None of them are probing the cloud particles directly with a probe in the atmosphere. So I've been leading a concept study to go to Venus and to revisit some of the issues that I mentioned, because a theory is just a theory, right? No matter how crazy or solid your hypothesis is, we need actual data. I'm really pleased to tell you that we are going to Venus on a mission with the Rocket Lab, with Rocket Lab. Rocket Lab is planning a launch in 2023. Rocket Lab will launch a rocket with a cruise vehicle that will drop a very small probe into the atmosphere. Okay, this slide is out of date. Our payload is up to 1 kilogram in mass. The probe will go through the atmosphere and last about an hour, but it will take measurements while the probe is in the clouds. There's no parachute. So during the cloud, in the 20-kilometer vertically thick cloud layer, there's in the 20-kilometer thick, it's just going to last for 3 minutes. And we're going to, search for evidence of life in the clouds. What we're going to do is have a tiny instrument. We call it an autofluorescing nephelometer. That's a lot of words. But autofluorescence is a way to detect organics inside cloud droplets. On Earth, many organic compounds fluoresce when subject to an ultraviolet light. So we're going to have a little instrument with a laser. It'll shine this laser light out of a window in the probe. And if there is anything interesting, it will fluoresce. Of course, this doesn't mean there's life there. It could mean that there's this organic chemistry starting from simple organic molecules in concentrated sulfuric acid, but it would sure be interesting and motivate us to go back for something more detailed. This autofluorescing nephelometer will also measure the backscatter light into a certain angular range of both intensity and polarization. And from that, we'll be able to tell something about the shape of the particle. We'll be able to learn the shape of the particles and the index of refraction, which will help us understand the composition. We're very interested in these mode 3 particles of unknown composition to see if they might indicate even like a habitable environment for some kind of life. Okay, so this is a little picture, and you won't have time to read all of this, but it's a little picture and table of a commercially available instrument that goes on the outside of aircraft and does what I was telling you. It does it doesn't do the fluorescence, but it does the backscatter. And this is done by Droplet Measurement Technologies, who is building the instrument for our mission. So switching topics for a second, we also in our study came up with a medium mission where, reminiscent and inspired by the Russia Vega balloons that went to Venus in the late 1970s, we would send a balloon to Venus. And this balloon would last for about a week or so, maybe 2 weeks, and it would have very specific measurements. The one we're really most interested in is to actually understand the acidity, the pH of these droplets. Because if they're not as acidic as we thought, either by salt, particles being uplofted or life neutralizing its environment, we really want to know about that. We'd like to really detect the amount of water vapor, because right now the atmosphere is so incredibly dry. We'd like to know if there are pockets with higher humidity. We'd like to detect and identify metals in the cloud particles, because as we talked about before, metals are needed for at least life here to catalyze reactions. Okay, there's a lot more here. I want to wrap up so we have time for a bit of Q&A. But I want to tell you how excited I personally am for a series of astrobiology missions to Venus. If any of you have interest, please get in touch with me. We're confident we'll do the first mission. We will get to our medium mission. It's more pie in the sky that a large part of the community is interested in sample return. We know about Mars, people talk about other bodies, but we could go to Venus and do a sample return, not of the surface, but of the atmosphere, which is very challenging and hard. We can imagine bringing home some of the cloud particles so we can really see what's going on. So in conclusion, I would like to thank the sponsor of our study, Breakthrough Initiatives. And there's thanks here to a number of small space companies who helped out with a lot of the instrument and engineering thoughts. So our goal is to go to Venus to measure gases, to look at the droplets, and to see if there's any chance that Venus is habitable or any signs of life on Venus. Thank you for your attention.
Thanks a lot, Dr. Seager. And we'll move into the Q&A. The first question is, Dear Sarah, if life does exist on Venus, how would life be restrained by the conditions of the atmosphere from developing into so-called complex forms?
Sorry, I was just reading a different question, so I didn't hear that. What is the, oh wait. Okay, so there's a lot of reason why, well, we're not experts, right? No, none of us know what's going on Venus. However, it's very nutrient limited. Like think about life here. We have tons of nutrients, right? We have stuff running off from the land into the ocean, lots of minerals, lots of metals. This atmosphere, as far as we know, is like starved for things. So that's probably the main reason life can't evolve into something more complicated. While you're thinking of the next question, I do want to ask this one about, it says from Simon, when I did A-level chemistry, the impression I got was that spectrometers proved beyond a doubt what a compound element was. Given the debate over phosphine on Venus, I presume that is not the case. A lot is open to interpretation. So there's a mass spectrometer and there's like a gas spectrometer. For the mass spectrometer that went into the atmosphere of Venus on Pioneer Venus, what that does is it actually ionizes the compounds and then subjects them to a magnetic field. And based on how they're deflected, it can tell something about the mass. And in that case, we see the parent ions. And so you have to piece together what's the most likely compound that the parent ions originated from. With respect to, I didn't give the whole talk on phosphine and how we detected it. With actually radio telescope, it's measuring an absorption feature. And you know, if you are confident and believe that there is a signal there, you have to ask yourself, what other molecules can it be absorbed at the same wavelength range? Now, in this case of this radio telescope, we only saw one single line from phosphine. Usually you want to see many lines so you can robustly associate it, like you say, prove beyond a doubt what compound element it was. In this case, we only have one line, and there is some push that it's not phosphine, it's sulfur dioxide, which unfortunately has an overlapping feature. So in the clean lab, when you can get as much information as you want, maybe it's you can say something beyond a doubt. Okay, I'll turn it back over to my moderator.
Wonderful, thank you. Let's throw it to Altspace VR. Right now, they have someone who's ready to ask a question from the virtual reality space. So Altspace VR, take it away.
Thank you so much, Sarah. I wanted to ask you, I understand that we've seen no meteorites that we know of that have come from Venus, unlike Mars, where we've seen quite a few. That makes me wonder, would the sample return mission be significantly more difficult than what we just initiated with the Mars sample return missions? Would there be greater need for fuel or anything of that nature? Could you talk a little bit about that?
Sure, yeah, we probably wouldn't need a greater need for fuel, but we're not intending to go down to the surface of Venus because we're interested in the atmosphere, and down at the surface, there's like a much higher pressure and the gravity is much higher. Actually, the gravity of Venus is much higher, so we will need more fuel. The main challenge is we want to capture part of the atmosphere and launch like from a balloon. And that really hasn't been done before, although there's some small companies wanting to do something like that here on Earth. So, you know, probably I don't know, in my mind personally, I mean, there's a lot of challenges, but I don't think it's more challenging than our Mars sample return. And indeed, we'll be borrowing heavily from that.
Excellent, thank you so much.
All right, next question is from Stephen, and Stephen say, can you give us a mass balance estimate? How much ammonia is required to reduce the pH of concentrated sulfuric acid to between 1 and -1?
Okay, so unfortunately, I don't have that number in my head. I'd have to look up my paper, which I don't have time to look it up now. You need a lot of life, but not, you know, like I could, yeah, I don't have that answer for you right now, but I could look it up and give you an answer if you email me the question.
Thank you. So a question from Jeff, how much will the 2023 probe mission cost and how will it be funded?
This so far is a privately funded mission. The bulk of the cost is funded out of Rocket Lab. They have I don't know how Rocket Lab is funding this. I'm just assuming that they have a private donor. We're right now, we're actually still raising money. So we have funding for the instrument, and we have a couple other things we're still trying to get money for. But this is, so far, it's a purely privately funded mission.
Thank you. Next question is from Moxon. They say, what Venus atmospheric measurements are possible from Earth orbit? Can you look through the Venusian atmosphere while it's moving across the sun from our point of view?
Yes, actually, you can do that. That's called a Venus transit. The transit happens in pairs, unfortunately, only every 120 years. And the last time it did this wasn't that long ago, it was 2012. So if you're like one of those biohackers for longevity or can find a way to live a long time, you could do that in the future. Now, it's hard to observe the Venus atmosphere from here because the clouds are so incredibly reflective and they make a kind of barrier to really see what's beneath. You know, we've tried to search for phosphine gas at infrared wavelengths instead of the radio wavelengths where our detection is, and we haven't had any success because we can only see above the clouds actually. So we can do stuff from Earth. People do measure sulfur dioxide, they measure water vapor, but we really want to send a probe into the atmosphere to make some gas measurements. And NASA, one of the missions, Da Vinci, is going to send a probe down and measure some gases.
Great. So we have 1 minute left, but maybe there's time for like one more very quick question. Let's see. If there's anything you see, please feel free to answer. But if not, then I'll ask a question from Amit. And they say, should an orbiter be used for up-close spectrometry?
Yes, but it has, and they will do that. The new missions going to Venus by NASA and ESA will definitely be doing that. The thing is, we're very interested in the cloud layer. It's incredibly vertically thick, 20 kilometers. And it's I forgot to mention this earlier, but the clouds completely cover the entire planet. Not like here on Earth, where sometimes it's cloudy, sometimes it's not. Some areas are always cloudy, some areas are rarely cloudy. And so even an orbiter cannot penetrate the clouds for some gases of interest.
Wonderful. Thank you very much for the presentations and for answering the questions.